In this lesson, we're going to talk about frequency, rise time, and harmonics. And the first question we're going to ask is, how do we measure frequency? Here is a sample waveform. This is 1 second of time across the horizontal axis. This waveform is going through 3 cycles here. So there's the first cycle, there's the second cycle, and there's the third cycle. So we can say that this has gone through 3 cycles in 1 second, or the frequency is 3 cycles per second, now called 3 hertz. It used to be called cycles per second when I was young, and that was a nice intuitive measure. That is a measure of frequency we use, and we give it the symbol F. Another way we could look at this is count the number of degrees that we go through. So here's 360 degrees. Here's another 360 degrees for 720. Here's another 360 degrees for 1080. So we could say that this has gone through 1080 degrees per second, or 360 times f degrees per second. Fortunately, we don't use that measure. The third measure we could use is radians. Now, you recall from high school geometry, I hope, that the definition of a radian goes like this. If we take a length equal to the radius of a circle, lay it along the circumference, and look at the subscribed angle in between, that angle is called a radian. And there are 2 pi radians in 360 degrees. So if we count the number of radians we're going through here, there's 2 pi, there's 2 more pi for 4 pi, there's 2 more for 6 pi. We could say that this has gone through 6 pi radians per second, or 2 pi f radians per second. That is a measure of frequency we use in electronics, and we give it the symbol omega. And it's called the angular velocity. Omega is 2 pi f equals the angular velocity. Now, you might ask, why do we use this measure in electronics? And the answer goes like this. Electronics is a science of change. Remember, things happen when we have current, and current is the flow of electrons, and things don't really get interesting unless electrons are moving and changing. So electronics is a science of change. The mathematics of change is calculus, and the angular measure in calculus is the radian. So people like me, who are very comfortable with cycles per second, are stuck with this calculus measure of radian, and all electronic engineers have to be able to work in this angular measure. One more thing we want to talk about is the period. The period is the length of time for one cycle. And, appropriately enough, if we go through 3 cycles in 1 second, then we go through 1 cycle in 1/3 of a second, or the period is simply 1 over f, the cyclical frequency. Both measures of frequency and measures of period can be important to us in electronics. Now, second, let's look at rise time. Here is a waveform. It's going from 0 to 1, or from 0% to 100%. And rise time is typically defined as the length of time it takes to go from the 10% point to the 90% point on the change of waveform. Now, you might ask, why don't we use 0 to 100? Well, this is called the roll-on characteristic. This is called the roll-off characteristic. And different technologies, bipolar, CMOS, mechanical relays, and so on, different technologies have different characteristics at roll-on and roll-off. But they all have pretty similar characteristics in between those points. So when we use the 10% point to the 90% point, we're pretty much talking apples to apples, regardless of what kind of technology we're using. Now, you could say, why don't we go from 0 to 100? Well, when we get up here to this roll-off, since different technologies roll off different ways and they approach 100%, reasonable people can argue about when they actually reach 100%. And that's not a very certain measure. But It's pretty clear to everyone when we're around the 10% point and the 90% point. So that is the measure that we have settled on in electronics, and that's the most common measure of rise time. Fall time would be defined in exactly the same way. Now, there are some data sheets that define rise time between the 20% point and the 80% point. And you might ask why? Well, maybe that's appropriate for the technology that they are using, and maybe they're engaging in specsmanship because the time between 20 and 80% is shorter than the time between 10 and 90%. So I will leave that for another time. Now we might ask, is there a relationship between the period and the rise time, or the frequency and the rise time? Let's look at this waveform right here. It has a little period right here. And we could look at the rise time that is associated with that looks like this right in here. It turns out that the rise time is approximately 1/3 of the period. We can mathematically derive that the relationship is that the rise time is 1/pi times f. There are formulas that can lead us to this conclusion, but that is approximately 1/3 of the period. Now, this applies for sine waves or cosine waves only. But if we have any other type of waveform, for example, here's a square wave, which is what we kind of hope our clock signals look like, and here's an underlying sine wave of exactly the same frequency, well, obviously the rise times here are dramatically different between these two waveforms. So there's no particular relationship between rise time and frequency for waveforms in general. Only in the case of a sine wave or in special kinds of waveforms we may decide to look at. But in general, there's no relationship between rise time and frequency. Now, if we think about this as part of a clock signal, so later this is going to come back down again, and there's a frequency associated with this clock signal. And we look at this rise time, and we look at the waveform for which this rise time is 1/3 of the period. There is an underlying sine wave here that has a much higher frequency than the clock signal has. But we can think of this frequency right here, this waveform, is an integral part of the circuit because this rise time lies right along the edge of this. So we can consider that at least part of this signal is inherent in the clock signal that we're looking at. So this rise time is part of a much higher frequency component or harmonic of the fundamental signal. Now, the way we can look at that, at least one way we can look at that, is through something called Fourier's theorem or Fourier's analyses or Fourier series and so on. And I will paraphrase or give my little brief definition of Fourier's theorem this way. Every signal or curve, no matter what its nature may be or in what way it was originally obtained, that is, every signal or curve can be exactly reproduced by superposing a sufficient number of individual sine and or cosine waveforms of different frequencies or harmonics and different phase shifts. That is, every signal or curve in our circuits can be exactly reproduced with a string of sufficient number of individual sine and or cosine waveforms of different frequencies and different phase shifts. That's what we do when we go through Fourier analyses. Now, let's look at harmonics and make sure we understand what harmonics are. Here is a fundamental frequency. That's a frequency, and we'll assume it's the fundamental frequency. Here is the third harmonic of that frequency. This waveform goes through one cycle in this amount of time. This waveform has gone through 3 cycles in that same amount of time. Therefore, this waveform is the third harmonic of this waveform. And in general, the nth harmonic of a waveform is n times the fundamental frequency of the waveform we're talking about. Now, a square wave contains many harmonics of the fundamental frequency. Here is one way of looking at a Fourier series of a square wave. There are a couple of different ways we can do this. But a square wave of a certain frequency is equal to the cosine of that frequency minus the cosine of the third harmonic divided by 3 plus the cosine of the fifth harmonic divided by 5 minus the cosine of the seventh harmonic divided by 7, and so on. This is an infinite series that will stretch out in time. So we can get a better and better approximation of a square wave by adding more and more terms or more and more harmonics to this expression and summing them up. And UltraCAD has a little tool for being able to look at this. We call it the Fourier simulation tool. And I'm going to call it up and give you an illustration of that. And it looks like this. We're going to take a square wave from a cosine function. That's the same cosine function we had on the previous slide. We're going to take 99 harmonics, and we're going to tell this thing to calculate what the square wave would look like. And here is the fundamental frequency, the blue line. And here is the square wave that is derived from 99 harmonics. And it's a pretty good looking square wave. All right, well, let's just say we do 20 harmonics instead of 99. And we get something that looks like this. Now that still looks like a pretty good square wave. And I'll leave it up to you to decide whether that looks good enough for the particular circuit we're involved with. Let's do 11. And there is what 11 harmonics give us. And if we go to, say, 5, that's what 5 harmonics give us. And as we go fewer and fewer harmonics, the approximation gets worse and worse. Or as we use more and more harmonics, the approximation gets better and better. Now, one of the things you may not have seen as we went through this illustration is look at this rise time on this approximation of the square wave. And let's just change the number of harmonics from 5 to 50. Now watch what happens to the rise time as we change the number of harmonics. And it improves considerably. So here's the bottom line. Our systems need to be able to deal with the harmonics contained within our waveforms, not just the fundamental frequencies. And the reason is because the rise time determines the number of harmonics that are present. And if we want to pass the signal in a way that looks like we want it to look, we have to be able to pass all of these harmonics. So, for example, if you have a 1 megahertz waveform, you need to have a bandwidth of at least 11 megahertz to have a square wave that looks as good as what I showed you with the 11 harmonics. You need to have a 20 megahertz bandwidth to pass something that looks as good as our waveform looked with 20 harmonics, and so on. The bandwidth is determined by how many harmonics do we have to pass, and that determines how good the rise time will be in the system that we're designing. So here are the takeaways from lesson 1.3. First, angular velocity is an important measure of frequency. Omega is equal to 2 pi f, which we call the angular velocity. And then rise time is the issue for signal integrity, not frequency. And we're going to be emphasizing this over and over again as we go through these lessons.